What if air power no longer depended on pilots, but on machines that quietly changed the balance, becoming some of the most talked about systems in modern warfare? Not through one breakthrough, but through continuous engineering steps, each solving a specific limitation and pushing the design further. One of the most recognized starting points is the Bayraktar TB2. Measuring around 6.5 meters in length with a wingspan of 12 meters, it's relatively lightweight with a maximum takeoff weight of about 650 kilograms. Powered by a single propeller engine, it reaches speeds of around 220 kilometers per hour and operates at altitudes up to 27,000 feet. Its endurance is where it stands out, staying airborne for more than 24 hours with a range controlled through ground stations. It can carry up to 150 kilograms of precision-guided munitions mounted under its wings. Introduced into service in the mid-2010s, it gained global attention in conflicts like Libya, Syria, and Nagorno-Karabakh, where it proved the effectiveness of persistent aerial surveillance combined with precision strikes. But extended endurance alone couldn't solve everything. As operations expanded, range became the next limitation. The ENKA was designed to push beyond that. Slightly larger, about 8 meters long, with a wingspan reaching 17 meters, and a maximum takeoff weight of roughly 1,600 kilograms. It flies at speeds near 200 kilometers per hour, with operational altitudes up to 30,000 feet. What truly defines it is satellite communication. Unlike earlier systems, it can operate far beyond line of sight, extending its effective range dramatically. With endurance exceeding 24 hours, it carries advanced payloads, including electro-optical systems and radar, with a payload capacity around 200 kilograms. Entering service in the late 2010s, it has been used in cross-border operations and regional conflicts, providing long-range intelligence and surveillance. Still, increasing range created a new demand: more capability in the air. That demand led to a much larger platform, the Akinchi. With a length of about 12 meters and an impressive wingspan of 20 meters, its maximum takeoff weight reaches over 5,500 kilograms. Powered by twin turboprop engines, it can reach speeds of around 360 kilometers per hour and operate at altitudes up to 40,000 feet. Its payload capacity jumps significantly, exceeding 1,300 kilograms, allowing it to carry a wide range of mission systems and munitions. Endurance remains strong, with flight times around 24 hours. Introduced in the early 2020s, it represents a shift from tactical drones to strategic aerial platforms. Equipped with advanced avionics and radar systems, it supports more complex missions beyond simple surveillance. But even with this scale, one limitation still remained: speed. Speed is where the next evolution begins. The Kazil Elma moves away from propellers toward a jet-powered unmanned design. With a length of around 14 to 15 meters and a wingspan close to 10 meters, it features a compact aerodynamic structure. Powered by a jet engine, it is expected to reach near transonic speeds, significantly faster than traditional UAVs. Its operational altitude is projected above 35,000 feet, with a payload capacity of around 1,500 kilograms, carried internally and externally. First revealed in the early 2020s, it represents a new category, bridging the gap between drones and jet aircraft. Still under development, but already signaling a shift toward high-speed unmanned operations. Yet even with speed and power, another factor defines long-term success: That factor is reliability. The Kazil focuses less on extremes and more on consistent performance. Measuring around 6.5 meters in length, with a wingspan of approximately 10.5 meters and a maximum takeoff weight near 550 kilograms. It operates at speeds around 150 to 200 kilometers per hour, with altitudes reaching up to 22,000 feet. Its endurance allows missions lasting over 20 hours, carrying payloads close to 120 kilograms. What sets it apart is its triple redundant flight control system, ensuring continued operation even in case of system failure. Entering service in the late 2010s, it has been used in regional operations where stability and reliability are critical. Not the fastest, not the largest, but built to deliver every single time.
From lightweight surveillance platforms to high-altitude, high-speed systems, this evolution didn't happen overnight. It was built step by step through engineering choices that solved real problems. If you found this breakdown useful, a like and a follow on the Industrial Archive keeps these stories going, because this evolution is far from over.